Hi folks, Mr. Robeson here. Welcome to the last video of AP Calculus BC, Applications of Vectored Valued Functions. All right, so we're taking the things that we've learned in the last couple sections with derivatives and integrals and how vectored valued functions work, and we're just putting it together. So we already went over our position was our original vector, our velocity is the derivative, our acceleration is the second derivative, which is also the derivative of velocity. And we just take the derivatives of each part separately, like of each part of the vector, like the x part, the y component separately, and that's how our derivative works. If we want speed, that is the magnitude of velocity. So I mentioned magnitude in the very first one, and I said it was just the Pythagorean theorem. Well, that's literally what we're just going to do here. It's the Pythagorean theorem. We take the x component of the velocity, which is the derivative, squared, and the y component, which again, the derivative, and square it, and we take the square root of that, and at any given t value, that would give us the speed. If we just leave in t, that gives us a function for speed at any given t value. If we want to know the total distance traveled from A to B, we need to know what's our speed, and then we integrate that from A to B. So it really is just like the arc length. So if this formula looks familiar, this is exactly the arc length formula for parametrics, which makes perfect sense because the length of the curve would be the total distance that the curve travels, or a particle travels, if it's going along that curve. All right, if we want to know position from velocity at a point, well, what we do is we say, what's the total change, like the total displacement, which is, I guess maybe we should say displacement first and then go back. If we want the displacement, we say, how does the velocity changed over the integral from A to B? We integrate from A to B over the velocity. So that's the total accumulation of the velocity. That will tell us how we've moved over that interval. If we want to know a new position based on an old position and the velocity, we integrate the velocity, we find the total displacement over that interval, which is this, and we add it to the original position. All right? By the way, this is just like the definition of like the integral here, because this would be r of t2 minus r of t1, and we just add the r of t1 over to the other side, and that gets it. All right, so let's look at some examples here. So for a particle with the position given by x of t and y of t, so this is position we're starting with for t greater than 0, the derivative of x with respect to t is 3t squared, and the derivative of y with respect to t is t times cosine of 1.5t. And this may be a calculator question. Find the acceleration at t equals 1.2. All right, well, x of t was the position. These two together would be velocity. I need one more derivative to get the acceleration. So I could say a of t is the derivative of this guy, which is what, 6t? Not a hard derivative. And the derivative of this guy. Well, I got a t here and a t here. I've got to do a product rule. So it's first times derivative of cosine, which is negative sine of 1.5t, times derivative of the inside, so times 1.5, plus the second times derivative of the first. Derivative of t is just 1, so we get cosine of 1.5t. And then we're just going to plug in 1.2. So the acceleration at 1.2 is 6 times 1.2. And then this would be 1.2 times, let's see, we'd have negative 1.5 sine of 1.5 times 1.2 plus cosine of 1.5 times 1.2. And we would just be plugging that into our calculator to work that out. I guess we probably have time, and I haven't turned on my calculator yet. Well, shucks. All right, there's my calculator, and I can just type in each part separately. I can do 6 times 1.2, and there's the first component. For the second one, I'm pretty sure I'm already in the radian mode, but yeah, I am in radian, cool. So we'd have 1.2 times negative 1.5, sine for the first one, sine of 1.5 times 1.2, plus cosine of 1.5 times 1.2. I guess I don't need another set of parentheses there. 1.5 times 1.2. And there we go. So I've got 7.2 and negative 2.055. 7.2 comma negative 2.055. If we truncate, if we round, of course we'd have a 6 at the end. But there's our answer. That is our acceleration at time t equals 1.2. Kind of messed up my, there we go. All right, next up, if we want to find the speed at t equals 1.2. All right, well, speed, here's our speed right here, is the magnitude of the velocity. Well, these are the components for velocity already. They're there already. So our speed at time 1.2 would be the square root of the x guy with 1.2. So 3 times 1.2 squared, that quantity squared, plus our y guy at 1.2. 1.2 cosine of 1.5 times 1.2 squared. All right, and that would give us our speed. So again, it's just some calculator work from here. Second square root, and we've got some parentheses, 3 parentheses 1.2, close that, squared, and then this whole thing is going to be squared. There we go. Plus parentheses 1.2 times cosine of 1.5 times 1.2, close that, squared, and that's the end of the square root, yep. And we get our answer. Our speed is 4.328. And there we go. And if they gave us some sort of units, we would include the units. So this is the speed at t equals 1.2. I'm assuming that'd be seconds, but they didn't give us any units. All right, so just one more slide here, and that's it. So position of the particle is given by r of t equals, here's our first function, here's our second function. So 3t squared plus 2e to the t and 5t minus 3 sine t. Find an integral expression for the total distance traveled from 1 to 3. All right, so total distance traveled, if we go back and look, total distance traveled, it's this one right here. From A to B. It's the integral of the speed. So we're going to have the square roots in there. All right, so this was r. So that means we need r prime. We need our velocity. Velocity equals r prime equals, derivative of this guy is 6t plus 2e to the t. Derivative of 5t is just 5 minus 3. Derivative of sine is cosine. So there we go. There's our velocity function, velocity vector valued function. So that means our total distance equals the integral from 1 to 3 of the magnitude of that velocity function, which would be the integral from 1 to 3 of the square root of the first guy squared, so 6t plus 2e to the t squared, plus the second guy squared, 5 minus 3 cosine of t squared dt. All right, and it just says find the integral expression, so here is the integral expression. All right, next, find an integral expression for the displacement from 1 to 3. Well, if we go back here and look at the displacement, that's just the integral of the velocity function. So we just want the integral of v of t dt from 1 to 3. Well, again, v is this vectored valued function right here. So that is the integral of each part separately. So from 1 to 3 of 6t plus 2e to the t dt, comma, then the other part is the integral from 1 to 3 of 5 minus 3 cosine of t dt. And there we go. There's an integral expression for the displacement. All right, next one here. Let's switch some colors. I think this is the last problem. For the position of a particle given by, all right, so we're using basically parametric equation, but again, it works just like vectored value, x of t, y of t. For any t greater than or equal to 0, the derivative of x is 4t plus 2. The derivative of y is cosine of t squared for t, and for t equal to 0, we've got this point here. X of 0 is 0, y of 0 is 2. Find the speed. All right, well, the speed was the square root of the x guy squared at that point. So it'd be 4 times 2 plus 2 squared plus the y guy squared at that point. So it'd be cosine of 2 squared, so cosine of 4 squared. All right, and we would just plug that into the calculator. Let's see, that's 8 plus 2 is 10, so that's 100 plus cosine squared of 4. I don't know what cosine of 4 is. So second square root, 100 plus parentheses cosine of 4, close parentheses, close the other parentheses, squared. And there we go. It's just a little bit bigger than 10, 10.021. There's our speed. Find our acceleration. Well, this is the derivative of position, so this is already velocity. We need to go one more if we want acceleration. So our acceleration function will be, and I like to read using this form. So the derivative of 4t plus 2 is just 4. Derivative of cosine of t squared, well, the derivative of cosine is negative sine. We leave the inside the same. Then chain rule says times the derivative of the inside, so times 2t. Now we just plug in the 2. So the acceleration at 2 is, well, that's going to be 4 still. It's going to be 4 there, negative, so negative 4. Sine of 2 squared is 4. So there we go. We can leave it like that, or you can plug it in your calculator. Either one's fine. Finally, find the position at t equals 2. All right, well, if we're given velocity and we want to go to a position, we need to integrate. All right, so we need to do the integral of, let's see, 4t plus 2 dt, and the integral of cosine of t squared dt. Now, this first one's not so bad. We could do this integral. The second integral, cosine of t squared, we can't really do. All right, so what we're going to do here is we're going to do our little trick. And if you want, we can go back and look. It's basically this trick right here. So we do a definite integral instead of the indefinite integral. And we just add in the initial condition. And then that will give us the final condition. Or the final value, I guess we should say. So we're going to go from... So we want position at 2. So we're going to go from, we know it at 0. So we're going to go from 0 to 2. And we're going to add to this our initial position, 0. And this one's also going to go from 0 to 2. And we're going to add to it our initial position. So plus 2. And then we just got to work out each of those. So I'm just going to go to the calculator. So math 9. We're going from 0 to 2 of 4, well, we can use x instead of t. It looks like I'm using theta instead. Oh well, plus 2 theta. All right, cool. We get 12. All right, to do the other one, we've got that plus 2 in front. So we've got 2 plus math 9, the integral from 0 to 2 of cosine of our variable squared. Looks like we're using theta, no worries. D theta. All right. And there we go, 2.461. And that will be our position at time 2, given that we knew it at time 0. So we took where we were at 0, we added the displacement to it, and that gave us our position at 2. All right, so there we go. Applications of vector-valued functions. Check out the homework. And that's it for me for videos. So signing off. I'll see you guys in AP Stat maybe. Who knows?